Welcome everyone for this October SIPTA Seminar given by Ryan Martin. So we're very happy to welcome Ryan for this month's seminar. And without further ado, I will hand over the microphone to Enrique Miranda, who will chair scientifically the seminar. So Kike, I will let you introduce Ryan in a bit more details, and the floor is yours.
Okay, thanks, Sebastian. Well, so it's our pleasure today to welcome Ryan Martin here. As you know, he's a professor at the North Carolina State University. He was formerly at Purdue and also at the University of Illinois. Well, he's an expert on many topics on the foundations of statistics, on statistical inference with imprecise probabilities. That will be the topic I think he will be presenting today. He has published, well, over 100 papers and a very interesting book on inferential models, reasoning with uncertainty. He's a co-founder of an initiative that is called the Researchers One, that probably many of you are familiar with. If not, I suggest that you can check it out. And he has received a number of awards: the D.D. Mason Award, the Sigma Xi Scientific Research Honor Society, and also quite a few teaching awards at several universities. And actually, well, you could be saying, well, coincidence, and you will see that no, because he's actually a wonderful speaker, and it is our pleasure today to have him here talking about inferential models and the imprecise probabilities. So, okay, just with this, Ryan, the floor is yours.
Thanks for, well, first in the invitation to come and speak, or I guess to sit here and speak. Yeah, great to see some folks in the Zoom call, and thanks for a nice introduction, Kike. Well, let's see if I can deliver based on all of that hype. So yeah, so today I wanted to talk about well, something that actually I see Teddy's here, so he mentioned this. Kind of, at least to me, was an unknown paper by Fisher about what he called the underworld of probability. And so around the time he mentioned this to me, I looked it up, and I started thinking about this. And so this is really the result of just a few months of kind of thinking about this topic and how it's related to statistical inference and what I'm calling here this kind of like a behavioral and statistical reliability balance. So let's get into it. So I don't know, I like to start with some lines from people who have more authority than me, so that at least I don't have to motivate kind of why I'm thinking about these things. So I got a few quotes here from Jimmy Savage and Don Fraser and Brad Efron. I'm not going to read these out loud, but these are all basically about, there's sort of two ways of thinking about probability and about statistics, and that in many ways they don't agree. And so, you know, this kind of creates some need for trying to come to some kind of like consensus, some kind of balance between these two perspectives. So I think that this is important. I mean, in part because, you know, it's, I think, related to the identity of statistics and what is our contribution. And so we should be experts, I think, based on our 100+ years of experience. We should be authorities on uncertainty and how do we quantify uncertainty. And in many ways, we're not sort of delivering on that. So I'd say in many ways, we kind of sidestep this question. And so here's a line from the ASA President's Task Force on Statistical Significance. And they say something like different measures of uncertainty can complement one another. And that's really kind of an empty statement, it's more politically correct than really than it is helpful. It's just trying to say, well, everybody's right. And then this is just kind of a joke, but there's this sort of common meme about statistics that well, it just means never having to say that you're certain. So I think that this kind of lack of answers to these fundamental questions kind of creates some confusion and even some distrust. And so, you know, it's fine if there's some you know, if we don't know the answers, right? So not knowing the answers isn't such a big deal, but not having motivation to find those answers, I think, is a problem. And I'll defer again to Don Fraser about this as just complacency in the face of contradiction. Maybe it's not acceptable for some kind of central discipline of science. So along those lines, so I guess what I'm interested in is trying to find this balance. And so whether I can do it or not, I guess is still up in the air, but that's I guess what I'm after. So if you get down into this, and maybe this is an oversimplification, but ultimately these kind of problems boil down to some kind of competing priorities. And so I guess I'd argue here about behavioral reliability is more on the Bayesian side and statistical reliability is more on the frequentist side, and that these things don't quite agree, at least not in all cases. So if neither one of them is fully satisfactory, then I guess we got to look for something else. And so that's, I think, what I'm after. But of course, it's not clear at all what should this balance look like. And so I guess a couple of kind of basic claims here is just that, well, I think that imprecision is actually inherent to finding this balance. And so it's not about imprecision that we introduce, it's that it's already there. And so I think that it's the right thing to do is to try to acknowledge that and make use of it. So this is a great opportunity, I think, for both for statisticians, but I think also for imprecise probability communities. All right, so what am I going to talk about? So I thought, well, let me draw a picture and kind of say a few words about this, and then I'll try to sort of piece these things together. So inside of the gray box that's there, these are things that I'm going to call inferential models that happen to satisfy a no-sure loss type of property. So maybe the big rectangle, the whole like slide is like all of the inferential models. Some of them are satisfy some no-sure loss. Some of them I should say, so no-sure loss is something familiar to you folks. The next inside box, these are inferential models that are valid. You may not know what that is. I'll tell you something about that later. And then inside the blue box, there's a couple of circles. And so these circles are labeled with some properties that you probably don't know about. I'll tell you about those things. So what I'm trying to get at is kind of zooming in on some things. And I hope that something in this middle part is where we can find this balance. Okay, so one of the things that maybe is familiar to the community that's here in this talk is this one spot here. This is the generalized Bayes rule. So that's a special kind of inferential model that happens to sit inside some of these things, right? So it's inside of this thing I'm calling invulnerable, but it's outside these ones I'm calling here strongly valid, but inside the others, right? And so what I'm hoping to do is to eventually be able to explain to you something about what's inside this middle part. So we'll see what we're able to come up with. Maybe let me put the chat up here in case there's something comes up. Okay, so I said in a picture kind of what this is about. Let me kind of say a few more things in words. So what I want to talk about first is this Fisher's underworld and how I think there's some new perspectives maybe that can come out of this. Then I have to give you some background about what these inferential model things are. I mentioned in the picture you saw it, this notion of invulnerability. So I need to tell you what that is and how it's somehow connected to this generalized Bayes type of idea. Then I want to sort of make some transition sort of more towards this kind of balance. And so this will be where this kind of validity, and I'll try to explain what I mean by this minimal vulnerability. Then I want to say a few things that's a little bit of a tangent, but I want to talk about this strong validity and what I'm calling now these possibilistic IMs. And that'll then lead to some final conclusions. So I wanted to put this here just so that because I'll forget by the end, is that I have a few things that I'm going to say that I think are new. I think there's probably more questions here than answers, though. And so part of the reason why I wanted to do this was that, well, I can get the things out there. You guys probably know more than me on various things. And so maybe you have some suggestions, or maybe there's some nice opportunities for collaboration. So, please feel free to, I mean, it's maybe weird now to try to chime in during the presentation, but afterwards, if you have questions or whatever, you want to reach out to me, email or something, be happy to talk more. Okay, so what is this Fisher's underworld? So there's too many words on this slide, but I'll try to summarize this briefly. So what Fisher was talking about, he gave one kind of concrete example, and this was about have a six-sided die, and you're going to just throw the six-sided die. And so one of the faces on the six-sided die is called an ace. Okay, and so now I've listed here, there's three agents that are kind of considering this problem, agent 1, 2, 3. So agent 1 is in the textbook realm. It says that, well, agent 1 is going to say, well, I think the probability of tossing ace is, say, 1 out of 6. And so then that agent is going to be willing to accept some bets against this ace at some, let's say, odds 4 to 1. All right, so this is a standard kind of textbook type of situation where you know the probability, then you know the odds, and everything is fine. Okay, so agent 2 now is at a different position, right? So agent 2 is going to look and say, well, what is agent 1 doing? Do I think what agent 1 is doing is reasonable. Okay, so just as an example, so maybe this agent 2 says, well, I think that, you know, at least 10% of the dice that are in the box that agent 1 is going to go and grab his die from has probability greater than or equal to 1/5 of throwing A's. So then the agent 2 is going to say, well, I think agent 1 is wrong. And so then they're going to formulate their own odds about whether agent 1 is going to be successful. So what agent 2 is going to be doing is betting against agent 1. So he's not betting directly on what happens on the die roll. He's betting against the success of agent 1. Okay. And similarly, you can keep going down. So if this, I'm stopping here at level 3, but this could continue to go down. And so here is exactly the way Fisher describes this. It says, well, at the 3rd level, agent 3, he doesn't know or even think he knows about the probability of throwing ace, but he knows something. And so the thing he knows is about maybe the consignment of boxes that are going to be used from which a die is going to be chosen, right? So it gets very sort of murky here in very Fisher style. But at the end of the day, he says, well, I have some confidence about the odds at which I would bet against the success of agent 2. Right, so agent 1 is betting about the outcome of the die roll. Agent 2 is betting on the success of agent 1, and agent 3 is betting on success of agent 2. Right, so you see that this is creating some kind of layers or levels. Okay, and so the thing I wanted to, I guess, to draw your attention to is like agent 2 and agent 3 are not actually writing down probabilities about the die turning up ace. Right, they're basically giving some kind of bounds, right? And so because they have these bounds, then they're able to make some judgments. Do I think the person at the level above me is right or wrong, right? And so somehow there's an imprecision sort of notion here, because the people at levels 2 and 3 are not formulating precise probability statements about the probability of tossing an ace. It's about something else, and so it's of course is related, but they're not doing a complete specification of their beliefs in a probabilistic type of way. Okay, so if you find this paper and you try to read it, right, it's, I guess, effectively impossible, because in very Fisher form, this is quite cryptic, and there's like it's really hard to get some kind of idea of what he's actually saying. So I found this quote, or it's not really a quote, but this from Frank Hampel has a paper talking about reading Fisher. It says, you don't understand Fisher, you just feel what he means. I felt like that was a good description of what my experience looking at this Fisher's paper. But in any case, so here's, I guess, the way I see it is that probability has different levels. There's the top level, which is the textbook kind of setting where we know the odds, and this is how we decide about bets. But the deeper levels, they know less, right? So they assume some different things. They have different objectives. They know less, perhaps. And so what they're doing, they're not actually betting on the outcome of this experiment or this trial. What they're doing is they're really scrutinizing the quality of the probability statements by the people above them. Okay, and so, well, I already mentioned some clear hints about imprecision, but what does this have to do with, like, let's say, statistical inference? Okay, so I was thinking about that. The statistician is at, let's say, I guess the way I'll present this is at level 2. So statistician is like at level 2. They're going to be making some kind of inferences, and so this is going to be based on some incomplete sort of information, but they get data, they have models, right? And they try to formulate some inferences. Then there's like this next level below, right? And this next level I'm going to call here like society, right? And so they're going to be doing some kind of scrutiny of the statistician's inferences, right? And so then what I was hoping for, and we'll see what we can do, is that that maybe there's this kind of balance can be achieved by thinking about trying to be invulnerable from the statistician's point of view, trying to be invulnerable to this kind of scrutiny by society. Okay, so let's so let's get into this a little bit more seriously. So as far as so what is our objective as statistician? This is from Ian Hacking, says that statisticians want numerical measures of degrees of belief to support to which data support hypotheses. So what does that mean? So that just means, well, I'm going to do something like formulate some kind of model. Then that model is maybe going to be related to some parameters. Then I want to observe the data, and then I'm going to convert that information into some kind of probability statements. Okay, so I'm doing things very general here. I guess partly for the community that I'm speaking to, you guys, this is what you do. So I'm going to start here with a model that describes beliefs about the pair y theta. So y is like data that I can observe. Theta is the thing that's unknown that I'd like to make statements about. So these like lower upper bar p's, these are just lower upper probabilities, coherent lower and upper probabilities, even provisions. Okay, so an example of what I mean here is that perhaps I have a precise model for y given theta. This is the typical statistical type of setup. So this maybe has a likelihood function, but then I can't quite specify my prior beliefs, so this would look imprecise. Okay? And so it could in fact be vacuous, that I literally know nothing about the parameter. Okay, so then the goal is, well, I'm going to observe y, and I want to quantify my uncertainty about theta. So then this step where I take the model and the data and convert it into some kind of quantification of uncertainty, this is the inferential model. It's just a function that takes data and other things into some new pair of lower and upper probabilities. So these are things, I don't need to tell you guys much about this, but ultimately, I mean, this is just a mathematical formula. How do I take data and map it into some kind of probability statements about the unknown? So I'm going to say that these are coherent lower upper probabilities, also provisions. This is for each y. And then there's a relationship between these two guys. So effectively, I only need to tell you one of them. Okay, but in terms of statistics, what's going to happen is that, I mean, this allows us to do probabilistic reasoning. So by that, I just mean that if the lower probabilities turn out to be small, then that tells us, well, we have some doubts about a hypothesis. If the lower probability tends to be large, then we have reason to, there's support for this kind of hypothesis. And so that's what I mean here by some sort of probabilistic reasoning. Okay, but in addition to that, I can also do things like to sort of peel off some kind of hypothesis tests or confidence sets or something like this, right? So I can do the more Bayesian type of reasoning with the actual probabilities, or I can do something more frequentist like with the procedures that I can derive from it. Okay, so there's, of course, many different types of inferential models. And so how do we make a choice between those depends on our kind of priorities. All right, so now we have a little bit of background. So let me try to go back to this underworld thing and say a few more words. Okay, so the statistician, I would say, is like Fisher's agent 2. So he doesn't know about the world. He doesn't know about theta. He may have some beliefs about it, which he can formulate in terms of model. He has data that he can observe. So then he wants to use that information. He's going to construct one of these inferential models. And so it's just going to be producing some kind of probability statements about the unknown. So then there's this other agent, I'm going to call it the scrutinizer. And so what the scrutinizer is doing, to kind of play in the role of like society. And so the scrutinizer is going to look for vulnerabilities in the statistician's inferential model, the idea being to sort of expose those vulnerabilities and in fact capitalize off of them. Okay, but I want to emphasize this is not about money, right? So it's sort of the scrutinizer's duty to society to hold the statistician accountable. So that was what I had in mind, and I've sort of backed off of the falsification thing that was in the title because that maybe has some other kind of connotations. But this is ultimately what I was interested in, is like sort of, statistician can write down any probabilities that they want, and there's no way to, you never see the truth, right? Data is never revealed to you, so you never see whether the statistician's right or wrong. So in some way, they kind of get to be, there's no accountability. So what I was interested in was kind of thinking about this underworld in that sense. Okay, so if we're thinking about the statistician is going to put forth probability statements, the scrutinizer is going to try to scrutinize and maybe to try to capitalize off of them. So of course, it makes sense that the statistician wouldn't want to allow this. You could argue that maybe the statistician doesn't care if this other agent is making money at their expense. But what will happen here later is that, in fact, it is money coming out of statistician's pocket, the way this can be formulated. Okay. So anyway, so what does it mean for one of these inferential models to be invulnerable? What does that actually mean? Okay, so let's think about this again. So in the underworld, this agent 3 thinks that agent 2's probability statements are wrong and somehow vulnerable to loss. So in terms of the notation we have now, let's just say without loss of generality, we can talk about the scrutinizer thinks that the statistician's support, this is like that lower probability to some hypothesis, tends to be too large. So tends in the sense as a function of y. Okay, so what the scrutinizer might do is then say, okay, well, they're going to say, well, let me pick a particular hypothesis in one of these kind of alpha values. Let's suppose that I'm able to find those things. Then I'm going to offer statistician this gamble. Okay, and the gamble looks something like this. Let's just call it W, maybe for winnings. Okay, so let's look at what's going to happen. So this is an indicator function. So this is going to say, scrutinizer is going to say, well, I'm going to look and see what the statistician's probability statement says, right? So if this guy tends to be large, right, greater than this 1 minus alpha specified, then this is now 1. And so then the cost of this kind of contingent gamble is one like this, that would say pays $1, €1 if the H holds. And so then you have the cost of this gamble is this 1 minus alpha value. Okay, so when this condition holds, this difference is, or at least what I'm trying to say is that this is to the statistician, this would be what I'm calling here an acceptable gamble. I guess in imprecise probability literature, I think you guys call this almost desirable. So this is with respect to the inferential model. So given data, the statistician is going to think this is an acceptable gamble, right? In the sense that the lower expectation is greater than or equal to 0. So this is, I apologize for the notation, but what I mean by this is that the y is fixed and this is averaging over the theta. Okay, so now where the statistician can have trouble is if this thing which is acceptable to him for every y turns out to be unacceptable in sort of the sense of, like, let's say long run, right? So averaging over y. Okay, so then here is what I mean by invulnerability, and also I guess indirectly about vulnerability, is that, so I've got statistician has their own model. So this is playing the statistician's game using their statistical model. We say that this the statistician is vulnerable, or the IM is vulnerable invulnerable if all of those gambles indexed by the hypotheses and about this kind of cutoff are acceptable, in the sense that the lower expectation of those gambles is positive. So this is for every hypothesis and threshold. So otherwise, this we say it's vulnerable. Okay, so I see some similarities to the coherence, like in Wally's book, or in the Yurt's and Mateus's book. But it doesn't, at least to me, I don't think it's the same. So this is usually looking at like partitions, and that you observe some event in the partition, and then you make some kind of updates there, and then it's protecting you from having, for example, like the prices that you're willing to buy or sell going uniformly up or down depending on the outcome of the experiment. So I see some similarities here, but I don't think it's the same, and that's maybe something we can talk a bit more about at the end. But I was thinking, like, so what does this remind me of? And so a long time back, when I was an undergraduate, I took a class in cryptography, and I remember this, I couldn't remember the name, but I remember this principle was this Kirchhoff's principle. And so in cryptography, this says, the strategy, or at least this principle says, assume that the attackers know everything about your encryption system, and you need to design it in such a way that it's secure even if they know. Right. So the idea is that you can't count on that the attacker is lazy or isn't willing to kind of spend the time to find out about what it is that you're doing. You assume that they know everything, and it needs to be secure anyway. So this invulnerability is basically that I can imagine that the scrutinizer is going to dig into the ways that I assign my probabilities, make my probability statements, and to dig into this and try to find weaknesses any way that they can. And so what I should do if I want to be invulnerable is just to protect myself against all possibilities, right? So to be secure, even if they know how to find, dig into my calculations and things like this. Okay, so whether this invulnerability is a strong condition, I guess it's not clear. It maybe sounds like it's kind of a strong condition. But at the very first, we should decide, is there anything that satisfies it? Is it so strong that nothing would satisfy it? Then it's kind of a silly thing to do. At least for folks in this, most of the folks here listening to this talk, probably the very first thing that you'd guess would be, what about generalized Bayes? Right. So generalized Bayes, I'm not being very, very careful here in terms of how I'm writing it, but this is, I think is familiar to folks, is that effectively what you can do here is you can imagine there's a collection of a bunch of joint distributions, right, for y theta. And so all this is doing, what we're going to do is we're going to find the Bayes posterior for every one of the joint distributions that's compatible with this imprecise model, and then do a max and min, right? So this is taking the infimum over all of those joint distributions for y theta, with doing Bayes rule to condition on the value of y. Okay, so this generalized Bayes IM actually is one that's invulnerable. So I showed you in the picture earlier that the GBR was one of the points inside of that circle. So that is, I guess, just a pictorial representation of what this what the theorem says, is that generalized Bayes IM is one that's invulnerable. So I don't know if there's other ones. So that's, I guess, is maybe still a kind of open question, is this the only one? And if so, maybe that's not a very interesting condition, but I guess I'm optimistic that there maybe are some other things. Regardless, I think that it is kind of neat to see. I mean, Fisher was, of course, not an imprecise probabilist, but kind of following, at least attempting to follow along his arguments, maybe gets us to something which is really central to imprecise probability, namely this generalized Bayes rule. Okay, so what I've said so far is really more on the behavioral side. At least it was maybe motivated by some statistical things, but looks more like coherence more on the behavioral side. So getting towards balance, I like the line here I found in Wally's book says, one difficulty with generalized Bayes is that the updated provisions are highly imprecise, right? And so even Wally is kind of backing off on coherence, or at least on generalized Bayes in this case, and saying, well, it's just one of the many possible strategies. So if now we're thinking towards balance, maybe we have some more flexibility where we're saying it doesn't have to be generalized Bayes because maybe generalized Bayes is too conservative. Okay, so while these things like invulnerability and coherence I think are nice, this, as Wally mentions, this tends to be too conservative, and so maybe it's too much of an emphasis on the behavioral side. Right. So just as an example, this is one that's, for statisticians, this is the most common situation, is where I don't actually know anything about the unknown parameter, the theta. I'm totally ignorant about the theta. So in this case, this is talking about like a vacuous prior. And for these problems, like a generalized Bayes doesn't work. You can't learn anything. You just get a vacuous posterior. And so this is not really an acceptable answer, at least from the statistician's point of view. So what other things might we be able to do? So if you've seen me give presentations about some of these things before, I've probably talked about this notion of validity. The notion that I had described before was probably one focused specifically on this vacuous priors. So what I have here in the definition on the slide is a generalized version of this, which accounts for the kind of imprecise prior distribution, a general imprecise prior distribution on the theta. Okay, so what this says is the following, is that, okay, the inferential model, that's this lower upper probability thing, right? So this is saying that, look at this event where I assign a relatively high lower probability to this hypothesis, and the hypothesis is wrong, right? So this event on the inside is somehow kind of like a bad thing. It's like an error in some sense, right? And so then all this condition is doing is to say, let's ensure that the error has low probability. Right. So that's a very natural, and I think a statistical type of idea, is that I'm going to use these things to assign beliefs or lower probabilities to these hypotheses, and I want that procedure to not have too many errors. It's a very frequentist type of thinking there. Okay. So it doesn't matter that this is just about that this has an imprecise probability here. In the old days, I used to show these things, and it would just be about a precise probability about y given theta. This is more general. Okay. All right, so I mentioned, I guess I explained these things about the kind of controlling error. So that seems very much like statistical. It's mostly statistical reliability considerations. So what about behavioral? Is there anything that we can say? Is there somehow a connection between this kind of statistical property of validity and these other things like no-sure loss and coherence? Okay, so one thing is that generalized Bayes is also valid, right? So the generalized Bayes, which is largely motivated by the behavioral properties, actually does satisfy this statistical one, which I didn't actually expect. So I thought that was actually pretty cool. But in fact, validity actually says a bit more. So I showed you in the picture how the validity square was inside of the no-sure loss square, because validity itself, whether it's generalized Bayes or not, this is strong enough to imply some kind of no-sure loss property. Okay. So I guess the way you kind of see this is that, well, validity maybe isn't such a strong condition. It doesn't, however, imply coherence, right? So basically it can't, because the only thing that really can be coherent always is generalized Bayes. And so generalized Bayes is not valid. So then there's some kind of disconnect. So what I see is that this validity property is sort of nestled in between like coherence, which is stronger, and no-sure loss, which is weaker. And so it's somewhere in between there. So I think that like validity maybe has some potential for balancing the behavioral side versus the statistical side. All right, so then I guess towards this, what can I say? So what I can say is that if we have something that's invulnerable, right, which was this thing about protecting myself from gambles that look acceptable that turn out to not be acceptable. Those invulnerable IMs are valid. Okay? So that is that. Take the kind of converse. So suppose something's not valid, right? Then there exists some pair of hypothesis and a threshold, such that you can sort of get the statistician to accept gambles, which will ultimately lose money in long run. Okay. So I was thinking about if there's a way to kind of describe this notion of validity in terms of sort of minimal vulnerability. I don't know if that quite works, but here I guess is the sort of summary, is that this generalized Bayes is one of the members inside of this collection of invulnerable things that is contained in the collection of valid things, which itself is contained in the collection of no sure loss things. Right. So if we were thinking about balance and maybe invulnerable is perhaps too much, perhaps it only has the generalized Bayes. Right, valids kind of is kind of in between these two things. So we wouldn't want to go so far as to allow sure loss, but anyway. So I guess the idea is that this validity sort of sits in between these two kind of conditions, might be the right thing for a sort of a balance. So one other thing to say, this is a little bit more specific than I guess maybe I wanted to be exactly, but I've probably talked in previous cases about this thing called a false confidence theorem. And so the original version of this false confidence theorem was focused specifically on the case with vacuous priors. And so what this one said is that there's a potential statistical unreliability if you use precise probabilities to quantify your uncertainty given data, like, for example, using default prior Bayes or fiducial or things like this. All right, so I remember at the SIPTA meeting, Michelle and Teddy talked about some kind of like issues about if you do some kind of non-probabilistic update. So using like the default priors to get a Bayes solution, or some kind of fiducial arguments to get this, so that things can go wrong in those kind of cases. And so in some sense, this theorem that I have on the screen here is kind of saying something similar, is that if you're considering focused on like vacuous priors, what's happening here is that the precise IMs are vulnerable. And the reason is that they're not valid. And so it's this vulnerability that is somehow related to it's the same kind of thing that's happening with this false confidence theorem. So that was probably too specific. I don't expect that folks here know the details about this false confidence theorem, but in any case, there is a connection, I think, between that result and this the theorem that's there on the slide. Okay, so we haven't achieved any balance yet because we've got some kind of competing things going on. And so in some sense, we haven't made any progress. Well, I've only told you about this generalized Bayes, which is mostly about the behavioral side. So then there's Corky Puppy. She has a good question, is what other valid IMs are out there? And so turns out this isn't so straightforward. And so the work that I have done previously was talking about validity. And so we have lots of these valid IMs for the case with vacuous priors. But this was something I hadn't anticipated until I got, didn't know about this until I got into these kind of more general types of prior beliefs, is that there's a difference between the kind of properties I was achieving before and the kind of properties in the case with this more general type of prior structure. So those things that I was doing before actually have a stronger property than the validity that I showed you on the screen, something called strong validity, which I'll tell you in a second. Okay, so what's happening now is that we had this nice connection between validity and this invulnerability. But if the focus is on something that's stronger, right, then it's not obvious that the invulnerable things are inside of the stronger condition, right? So the collection of strong validity, the collection of things that are strongly valid may not be contained or may not contain the invulnerable ones. All right, so now there's a sort of a disconnect that we need to try to understand. Okay, so then I guess a follow-up question to Corky's is, okay, so are there these good inferential models that are valid but not strongly valid? Right, and so this is a bit tricky. So I had attempted to work out this previously, and I consider this to be something of an open question, is that the idea that I had was to take a thing that is valid with respect to a vacuous prior and then try to combine it with a prior information. So using something like Dempster's rule or some other kind of like a possibilistic combination rule. And so this actually, like doing simulations and things, seems like this works, but I can't prove that it actually is valid. So I have some things in a paper about this. So if you wanted to check those out and we can talk, that I think that'd be cool. So I have some, I'm optimistic, but I haven't been able to work this to basically to settle this question. Okay, so if I have to go with my instinct, as a statistician, I guess my natural sort of instinct would be try to do the best I can in terms of the statistical reliability. Right. So I was thinking more from the statistical reliability side, what can I do that it would give me, I guess, what I consider to be the best possible results. So this took me on some kind of I guess, like unexpected journey. And this is into some things that I'm not going to talk about, but just some buzzwords maybe that are interesting, is that the using some kind of outer consonant approximations and this thing called the imprecise probability to possibility transform. So I end up using some of these kind of tools. And so I guess long story short, this possibilistic IM framework that I'm been pushing recently, this is able to do a number of things that I think are nice, is that this can incorporate the partial prior information out as I was describing. It's also likelihood based. And so, I mean, this is a bit technical, but many of the things that I had presented previously in other talks with the SIPTA group was actually the starting point was like data generating equations, like being able to write down how you would generate data. That's actually stronger than just having likelihood functions. And so the nice thing is that this framework doesn't require these data generating equations. You can just directly write down, you can use the likelihood function. So in the case where we have a precise model, but an imprecise prior, this is quite convenient. It works it's a possibility theoretic framework. So not by choice, that actually comes from some other considerations that I'm not going to describe, but the nice consequence of this is that things turn out to be relatively simple, especially computationally. So I say relatively simple, it doesn't mean it's simple, it's just relatively simple. This one will achieve this strong validity property, which I'll tell you about in a moment, and allows for some kind of adjustments for improved efficiency. So if you were at the SIPTA meeting this past summer, I did present something related to this possibilistic IM. I'm not going to say anything about it here, but just it is something that you would have seen before, at least if you were at the SIPTA meeting this summer. All right, so what does this thing look like? So let me just, to keep things relatively simple, let's talk about a precise model where there's a likelihood function and then imprecise prior distribution. So what this is going to do goes as follows: is that I'm going to construct this upper probability, the upper bar pi y. This is going to be a possibility measure. It'll have that kind of structure. Okay, and so what I want to do here is that the way this is going to be calculated, this is how all possibility measures look, is that there's some kind of contour function that drives it. And so the way you compute possibilities is just by maximizing this contour. So the particular contour in this case is defined this way. This is a lot of symbols going on here, but effectively this R is just like a likelihood ratio, relative likelihood. And so this is just doing an imprecise probability calculation with respect to the distribution of this relative likelihood. Right? If we were doing a vacuous prior case where I know nothing about theta, this would actually be a likelihood ratio. It'd be the likelihood divided by its maximum. This is more general because it allows the imprecise prior distribution to contribute. Okay, so I don't want to get into the details of this here, but let me just say is that this looks a lot like p-values, and in a way, I think this is the right way to think about p-values. In terms of practical things, right? This is a Choquet integral, which is not super complicated. So this is, at least I can do some computation, so it can't be that hard. But I do think that there's some room for improvement in terms of the computation. Okay, so anyway, so here is what the key property that this thing satisfies. And if you just kind of squint a little bit, what you'll see, this is basically looks like a p-value property, is that the thing being less than alpha has probability less than alpha. That's I guess is the main sort of takeaway in terms of what kind of properties we would be looking for here. The reason why something like this would be valuable is that in fact you can peel off some kind of nice things like confidence intervals. So if I can take this contour function, the little pi, and I cut it off at some level alpha, and then I say which thetas have contour exceeding this level alpha, then that is a confidence set in the sense that the probability that I miss the true theta is bounded by the alpha. right? And so, of course, this is with respect to the imprecise model here. So while it looks a lot like standard statistics things, this involves the imprecision in the prior distribution, and also covers the case where it's vacuous. So I guess I'm a bit slow on my presentation here, so maybe we'll skip some of this, but let me just say that I mentioned about generalized Bayes can't learn in the vacuous prior case, whereas this one, it can. So this is able to accommodate, in fact, very efficiently the vacuous prior case. There's something else that I was going to mention, but I think I'll probably just point to the reference here, is that the ability to do more than just test static hypotheses, I think this is something that's been recognized for a long time, and it's not clear how to do it. So I know that Deborah Mayo has a book and talking about these kind of things, that there's actually more that you can do with the classical sort of frequentist things than just, here's a sort of a naive null hypothesis, I can accept or reject it and then walk away. Actually, that's not how science works, is that you actually want to probe, right? So you test certain hypotheses, and based on the result of that test, you then ask further questions. So it's not just this one-off, like I ask one question, I reject or not, and I leave. So there's more going on to science and how statistics is involved. And so the classical frequentist things don't really get to that. So there's something more that's needed. And I think this this paper, this is my former student Leo, I think is here. So this one talks about how the imprecision itself kind of captures some of this, the probing aspect. And so I'll just leave it at that, because I'm running a bit short on the time here. All right, so what I wanted to do was to actually show you some pictures so that you could say, okay, yes, this is a thing that can be done, right? So this possibilistic IM is not just a fantasy. So these are relatively simple examples, but I wanted to show some pictures and stuff so that you can actually see it in action. So this is just simple binomial classical problem. So this is where I have a precise model, but an imprecise prior. And so what do I mean by imprecise prior in this case? In words, what I'm doing here is I'm saying I'm quantifying. The expert says I'm 90% sure that the success probability is less than 0.6, right? So I can take that information, I can quantify it as an imprecise prior distribution, then throw it into this possibilistic IM and crank it out, okay? So I have a picture, each of these pictures shows three different inferential models. One is where I've taken the vacuous prior, and I skipped over this bit about the efficiency bump. But now I've got two other cases with using this partial prior information. One is just using the direct thing, like the definition that I showed you. The other one is using this kind of efficiency bump. And so in the left, what you see, this is relatively small sample size. And so what's going on here is that the observation is actually that in this case, n is 8. So I've observed a count of 4. So the estimated probability is 0.5. That is consistent with the partial prior information. So what should happen is that we get some, at least when we're incorporating the partial prior, we get some benefit, right? Somehow it collapses things a bit more on the, like sort of towards what the data says, because it's consistent with prior. So you can see here is that the black one is where I just ignore prior information. The red one is where I incorporate it in this kind of basic way. And you see that the contour kind of tightens, at least on the right-hand side. This one where I kind of try to balance both, it doesn't concentrate quite as much, or it doesn't sort of shrink quite as much, but does a little bit, right? So this is incorporating the partial prior information in a particular way. Same story when you have a larger sample size. It's just now it's sort of less pronounced because the data sort of takes over a little bit more, but you see the same kind of pattern. So this can actually incorporate the prior information and make things in some sense more efficient. Okay, the same story here is just a different example about like kind of a trying to say, it's a clinical trial. That's what it's like a clinical trial type of setup where you have two arms with different kind of treatments, and you say, okay, well, count how many get better on this arm and how many get better on this arm. So in this particular case, not very many people got better, or not many people got worse. I don't remember the context. But in any case, so the idea here is that this one's more complicated because it's not just the binomial parameters, it's actually the log odds ratio of these two binomial parameters. So that requires some effort to do, but in fact, it can be done. And so the same kind of story here is that if you look at the what does this inferential model say about this log odds ratio, right? It's kind of pointing here, but if I use prior information that turns out to be true in this, or at least compatible with the data, I get a little bit of a benefit from that. So that I think is nice. Let me see about my time here. So I wanted to get back to the invulnerability stuff. So let me maybe say a little bit. Okay, I'm gonna skip this one too. So I had a couple of examples here, just kind of trying to highlight that I think what I think is, at least from a statistical side, is promising about this possibilistic IM. And so here's another example with like this Behrens-Fisher problem, where I think that there's some good things that can be done. But I'll skip over that. We can, if you have questions, I can talk about it. So I mentioned here briefly a few examples. These all look relatively simple because it's like low dimensions and classical type of statistical problems. Turns out you can do some similar things outside of this. So thinking about like prediction in supervised learning, or other kind of non-parametric type of cases where what you're interested in is these like statistical functionals. So my former student Leo is here. So here's a couple of papers about those things. I won't say any more, but just so that you know, at least those things are possible. All right, so let's go back to this, the underworld, Fisher's underworld. So where does this thing with like the possibilistic IMs and the strong validity fit in? Okay, so what we do know is that strong validity implies validity, which implies the no sure loss. So that's one thing that's given. This generalized Bayes rule, however, is not strongly valid. Basically, you have to be possibilistic to be strongly valid, which is why I like the possibilistic. So generalized Bayes rule can't be strongly valid, and so this kind of creates a separation. So what we can say is that invulnerability definitely does not imply strong validity. So the connection here is not so clear. And so what I think is the main sort of takeaway question, the key question here, I mentioned at the beginning that there's more questions than answers. The key question that you take away is that are there any inferential models that are strongly valid and invulnerable? So I don't know the answer, but that brings us back to the picture from before. This question mark here is that intersection between the things that are strongly valid, the things that are invulnerable. So we definitely know we can get inside of this blue box, and in particular inside of this red circle. Whether there's anything in the red circle that also have those the invulnerability, which was suggested maybe by the Fisher's perspective, I guess is still unclear. So let's I guess to wrap up. So remember the goal, right? So this kind of two theory Bayes versus frequentist problem, I think in some ways kind of threatens the identity of statistics. And so maybe we need to think about balance these two kind of considerations, behavioral and statistical. So I was started with this Fisher's underworld, kind of thinking about how does this relate to this kind of fight between, maybe I don't want to say fight, but this between statistician and society. And so somehow we want the statisticians and the probability statements they make to be, this should be accountable in some way. And so maybe this Fisher's underworld has something to say. So that motivated me thinking about this invulnerability notion. And so what, I guess in terms of the results I was able to say here, we can say that generalized Bayes is invulnerable. So there is at least one thing that's invulnerable. And also that invulnerability implies validity. So there's some connection, I think, between these various things. So I guess arguably there's some new connections here, I think, between Fisher and imprecision. But unfortunately, I still don't have a sort of clear answer to this. I think there's maybe some progress, but I think we don't have a clear answer. I did a little bit of a tangent about my this possibilistic IM that is at the moment is my go-to solution. I think has a variety of nice properties in terms of like strong validity. There's also the behavioral properties that are inherited from this. There's ways to get some kind of efficiency gains, which I didn't talk about. And then computation is not easy, but it is doable. There is extra structure that comes in these possibilistic IM. So it's not clear exactly where or how they're connected to this invulnerability notion. But ultimately, I think if we could find something that's in this intersection of the strongly valid and the invulnerable, then we would have found something like balance maybe that we're looking for. I guess if not, then if there's nothing in there, then I guess we have to keep looking. I don't know yet. Okay, so in terms of, I guess, a couple open questions, things that few of them I mentioned already, right? So this like, is generalized Bayes the only one that's invulnerable? Is there ways to construct inferential models that are valid but not strongly valid? I had some ideas, but I haven't, proof is still escapes me. Ways to improve on this kind of efficiency bump that I skipped over a little bit. And then, you know, whether there's these strongly valid IMs that are invulnerable. So that was kind of the main question. Other things that I think are sort of unrelated to the things that I mentioned here, but about efficient computations. So this, again, is a type of Shopke integral, maybe looks a bit specialized because of how the statistical parts contribute to it. But this is ultimately something that I think is doable, and there ought to be efficient ways to do it. I've been doing things naive so far. Those plots that I showed you are just my naive kind of attempts at this. There's opportunities for, I think, in this high dimensions cases. So this is something that I'm starting to get into now. I've been thinking about for a while, but just starting to get into this. But for example, like in the high dimension cases, there's of course an increased computational challenges. But more than that, there's a question about kind of thinking about how do we elicit this kind of thinking about it in terms of like prior information, but largely this is about regularization. So we're trying to elicit some meaningful or useful type of partial prior distribution that achieves the kind of regularization that is necessary for these high dimensional problems. Okay, and then I guess a more broad question is about actually model assessment and model selection. So that's something that hasn't been done yet, at least in terms of these kind of possibilistic IMs. So I have some thoughts about this, I think, that could be done. And so that's just an open question. So do I have like 1 minute or something? Is that, I think that's okay. Is that right? Sure. I'll just take it and then you can stop me if. So this is a little bit of a tangent, but I wanted to say something about this because, you know, this I think is specifically a spot where this perspective where we have, I guess the picture I have here is trying to show some kind of spectrum. And so there's, on the one hand, there's the sort of viewpoint that is typically called frequentist. And then on the other side, there's this other, you know, the other endpoint is like Bayesian. And so what distinguishes these is like their assumptions about the prior distribution. So on the Bayesian side, where you're sort of classical Bayesian, you have your prior. That's the one that's sitting there. That's the only one that's in consideration. Then there's, on the other side, there's the frequentist. And so for statisticians, we tend to think of the frequentist as no prior distribution, but that's actually not what's going on there. It's that, you know, imprecise probability folks know this, is that on the other side, the frequentist side, they just don't have information to rule out any prior. So, and in fact, they have every prior. So it's like the spectrum is kind of indexed by the how many priors are in play, right? And so in between there's where you can eliminate some priors, but not others. And so you're just left with some, and you need to try to deal with those. So in the classical problems, it kind of doesn't matter, because in some sense, like data is going to eventually overwhelm classical, I mean low dimensions. And so if the data ends up being kind of overwhelming the prior information, in a sense, it doesn't matter. But when you get into high dimension cases, you need this regularization. The regularization comes from somewhere. It doesn't come from the problem itself, that you have to put it in. So I think that it's in these high dimension cases where we really are in this middle part of the spectrum. And so thinking about it on the far left of the screen or on the far right of the screen isn't going to help, right? Because you don't really have what you need on the two ends, right? So I feel like that understanding about this spectrum and about the ability to incorporate this partial prior information, which is in this middle part, right, is going to allow us to actually have more satisfactory and maybe even more efficient solutions to these high dimension problems. So I'll stop here just to say, I guess there's my email, there's my website. So if you wanted to see some, some papers that I was mentioning, or if you have questions for me and you want to send an email or something, please feel free to reach out. So I'll stop there, and then we can do questions or whatever. So.